Hello, everybody. I am Scott Bednar.
And I'm Jessie Wild.
And we are very excited to bring you live coverage from Day 2 of NASA's Moon to Mars Ice and Prospecting Challenge. We are coming to you from NASA Langley Research Center in Hampton, Virginia, inside of their historic aircraft hangar.
You're probably wondering what's going on behind us. Well, we have 9 university teams who've traveled in from around the country to test their original technologies. So these teams are attempting to solve a lunar and Martian exploration dilemma, and that is how to extract subsurface ice and melt that ice into water.
This is not an easy challenge, but these teams do seem to be up to the task. So why don't we go take a closer look at their designs?
Let's go check it out.
Okay, great. So we have recently discovered what are thought to be large ice deposits under both the lunar and Martian surfaces. So these ice deposits could play a significant role one day in establishing a sustained human presence beyond our planet. I mean, imagine if you went to the moon and you could actually harvest the water and use it for drinking, for propulsion, or for other resources. The farther humans venture into space, the more important it becomes to manufacture materials and products using local resources.
That's absolutely right, and that's actually called in situ resource utilization, and we are going to talk about that a little bit later in the show, so stay with us. NASA is preparing to send the first woman and the next man to the moon in 2024. With new technologies and new systems, we're going to be exploring more locations across the surface than we ever thought was possible before. This time when we go, we're going to establish a sustainable human presence on and around the moon.
And what you're going to see today at NASA's Moon to Mars Ice and Prospecting Challenge actually represents an important step in human exploration of our moon.
Stay with us today as we tour how each of these teams has approached the challenge of harvesting water ice from beneath a simulated slice of extraterrestrial worlds.
Okay, Jessie, I think it's time to dive in a little deeper into this challenge.
Should we dig a little deeper?
Let's drill a little deeper.
Let's do it.
Okay, I want to show everyone at home one of these ice drilling systems up close and maybe give you a better feel for just how the Moon to Mars Ice and Prospecting Challenge works. So I'm going to step over here, and if you take a look at this big blue bin, you're going to see a whole bunch of these today. And that's because each team has one. What's inside? Well, we've got layers and layers and layers of different materials. The materials and the layers are a secret to the team, so I cannot tell. I am not a tattletale. But what I can tell you is all the way at the bottom of this big blue bin, we've got a giant block of ice. Ultimately, what teams need to do is figure out how to get through all of those mysterious layers, get to that ice, and get it out. They have to extract it. They need to harvest it and turn it into liquid water. If everything goes to plan, and hopefully it does, that water will begin to pool into a bucket just like this. And then later on, judges are going to assign point values to the teams based on things like how much water got pooled into the bucket or how clear the water is. Is it something you would want to drink? Yeah? Well, then you get more points.
But before they even reach that ice, they have another challenge ahead of them. They actually have to dig through several layers of what's meant to simulate the surface of the moon or Mars. They don't know what those layers are made of, how many layers they are, how thick they are, how dense they are. So they actually have to try to figure that out using drill telemetry. So they're collecting data with the drill that you can see right now, and they're putting that together in what we're calling a digital core. So that's basically a representation of their knowledge and understanding of what those layers are made of and how dense they are, how thick they are, and they're going to be judged on that as well. Well, before we go too far into depth with the teams and their technologies, let's go hear from NASA about the Moon to Mars Ice and Prospecting Challenge. Over to you, Scott.
Thank you, Jessie. All right, everybody, I am very excited to introduce you to Rick Davis. Rick is the Assistant Director for Science and Exploration at NASA. How are you doing, Rick?
I'm great, Scott. It's great to be here, too.
Great. So tell me, what have you seen so far at the Moon to Mars Ice and Prospecting Challenge?
So this is the 3rd year of doing this, as you know. It's very exciting because it's not only a really cool STEM event for encouraging students to learn about engineering and science, but it's actually, they're helping us push back the frontier of knowledge because they're pushing on technologies that we need to do to access the water at Mars and on the moon. And they are doing some new things this week that we have not ever done before, so it's very exciting.
So tell me about some of the things you've been seeing as you walk around the competition floor.
Yeah, so unlike a lot of STEM competitions, one of the things which we have really stressed in this particular event is building on the shoulders of giants. And the giants are the students in what came in the previous years. And so we have really collected and shared lessons learned, and what you're seeing that's really exciting is a convergence in the ways of accessing the ice that we have not seen before. And we're also doing some really cool things, because at Mars and on the moon, the amount of dirt on top of the ice, it's a complete, largely unknown. And they are understanding what it's made of as we go through this by looking at things like torques on the motors and that kind of thing. And that is really key for understanding what we're dealing with.
So the designs that are actually we're seeing here today could potentially one day be used in places like the moon or Mars?
Absolutely. In fact, our judges represent some of the most creative thinkers that are in this area. And they're here, one, because they totally believe that these students will be part of that solution, but they're also looking for ideas, and that is actually really cool.
Okay, so the fact that there is water on the moon or on Mars probably comes as a surprise to a lot of people. Can you just tell me a little bit more about that?
So I'll talk more to Mars because I know it better. But at Mars, there are whole, essentially buried oceans and glaciers. 10 years ago, 14 years ago, we didn't even know they existed. And now we do, and it's very exciting because we are finding large amounts of water on the planet. It's covered in dirt, or regolith as we call it. But it is an extremely valuable resource, and the biggest reason we need it is not an obvious one. The big reason is for the propellant for the trip home, and because we can make methane with that water, and that is really key for reducing the cost of missions to Mars. Eventually, there'll be other things like farming and all the things that all of us have water every day, like drinking water and all that kind of thing. But for right now, that's the big thing we're after, and it's large amounts. So we really want to understand how to access it efficiently so that we can get it and use it to drive the cost of these missions down.
It does come in handy, water.
It does. So. Well, and I would even say human beings are water-based creatures. We set up places, cities, and everything where there's water usually.
So maybe Mars and the moon is a good place to go.
Yep, exactly.
Fantastic. Well, Rick, I really appreciate your time.
Thank you.
And I'm going to throw it back to Jesse, who's out on the competition field. Jesse, back to you.
Thanks, Scott. For those of you just joining, we are live at NASA's Moon to Mars Ice and Prospecting Challenge, where university teams are drilling through simulated lunar and Martian soil and attempting to extract the ice below. One day, systems like these could be used to extract water from below the surface of the moon or Mars. And for future explorers, accessing water is going to be crucial for creating a sustained human presence beyond Earth. So let's go talk to some of the teams. The teams are up to some really, really cool stuff today. We're going to go start with the Colorado School of Mines. We have Nathan with us. Nathan, thank you so much for talking to us today.
Yeah, of course.
So can you tell me a little bit about your design?
Yeah, so the main point of our design is we have an auger that drills into the sediment, and we have a heat probe that after about an hour or two of drilling, once we get to the ice core, we stick the heat probe in, heat it up for about an hour, and start extracting the water through our heat probe. And so actually a couple minutes ago, we were able to extract about 5 liters of water in a matter of 1 or 2 minutes.
That's pretty exciting. Is that the first time you've collected water so far?
It is, actually.
So what was that like, getting the water in?
It was crazy because we ran into so many problems throughout yesterday of the competition. We had so many heating problems, a lot of wiring issues that the vibrations kept on causing. And to have that all pay off today it's crazy.
And so it seems like your team reacted to having these challenges. What was it like overcoming those challenges? How did you work through them?
A lot of it's just a lot of hard work, Everyone on the team they've spent so many hours, especially in the last few days. We brought our drill back to our hotel room on the 6th floor, actually. Managed to get it through the sliding doors, and we've been working on it pretty much in every single free second we have. And so it's been an experience.
Are you expecting to collect more water?
We are. So actually right now we're trying to get one more drill hole in with an hour and a half left. And so hopefully we can get at least another liter or two, ideally.
So you're racing the clock right now.
Exactly.
Well, thank you so much, Nathan, for talking with us. Good luck to you.
Yeah, thank you. I appreciate it.
I'm going to throw it back over to Scott, who's got another team to talk to. Back to you.
All right, thank you, Jesse. All right, we're going to go over and talk to my friend Brian at the University of Tennessee. How you doing today, Brian?
I'm doing well. How are you?
I'm doing wonderful. All right, so I see your machine is drilling. What's going on there here?
Yeah, we're trying to make it through this layer of concrete here. So our design is focused on a single integrated drill bit. So inside that bit that you see spinning there are both copper and aluminum pipes that sit stationary inside. And once we hit ice, those will extend down and melt and suck as they go.
So how close are you to hitting ice? Do you have any idea?
We're a little ways off. We had some trouble in the beginning with some of our electronic components and was causing us to run at only 1/5 of our motor's max capacity. So we've gotten around that a little bit, and now we're making some progress. But we'll see how it turns out.
So are you hopeful that you're going to reach the ice?
Yeah, we're hoping so. It's possible.
Once you reach the ice, what is your mechanism for extracting it and melting it?
So the copper pipe you can see up top extends down into the ice. It exits the end of this auger that you see spinning, and it has a heating element inside. So that goes down into the ice, away from the dirt and everything else, and melts it free of debris. A pipe inside of that extends from the bottom of that pipe and sucks that up through the end, through the center.
Awesome. So other than the drill, have you been having a good time at the challenge this week?
Oh yes, it's been fantastic. We've all learned so much. We're kind of a young team, and so we can take a lot of this knowledge moving forward and make some really great things in the future.
Awesome. Well, thank you, Brian. I wish you the best of luck. All right. Cheers. All right. I'm going to throw it back over to Jesse, who's somewhere on the competition field. Jesse.
Thanks, Scott. That was really cool to see. As we walk around the pit today, you're going to see that all of these drilling systems have a unique design. Each team is bringing a different idea to the table, and that diversity of ideas that we get from including students in a competition like this really helps expand our collective understanding. Now, today is day one of the competition, and teams are operating their drilling systems for the very first time.
That's right, and we've seen some very unique and interesting designs here. Most of the university students today are using a drill to dig through the simulated lunar and Martian soil to find that ice below it. But along the way to that ice, teams must collect data about the layers that they're drilling through. So things like how many layers there are, or how thick they are, or how dense they are. And they will use this information to create a digital core that they'll be judged on later in the competition. Okay, I want to throw it back to Jesse, who is actually with one of the competition organizers right now. Let's go learn a little bit more about how this competition came to be. Jesse.
Thanks, Scott. I'm here with Stacy Dees, who is actually the program manager for this challenge. So thank you so much for being with us, Stacy.
Absolutely.
Let's start off with, how is the competition going so far?
It is going amazingly well. Actually, just before I sat down, I was informed that the Colorado School of Mines has just collected about a gallon's worth of water, so that's really exciting. When we had this competition last year, we had a certain amount of water that was pulled over the 2 days. Yesterday's, just 1 day's total beat that. So that's pretty exciting going on.
That's awesome.
Well. I think probably the one word that I would use to describe what's going on today is adaptability. That's kind of the word of the day. Teams are really realizing that they have to reconfigure their designs and make changes to what they'd originally planned just because of what they're actually facing here. The reality of the competition is a little different than what they expected.
They're thinking on their feet, and we've seen a lot of that today as well. It's really cool to see.
Absolutely.
Now, how is this competition different from last year's? I understand there's an added component this year.
Absolutely. Of course, previously we were the Mars Ice Challenge, and now we're the Moon to Mars Ice and Prospecting Challenge. We've asked teams to develop a digital core for us, which basically they use digital telemetry on their system, things like penetration rate, depth, power, to be able to tell us where different layers are in the system. There's different layers of material in the overburden that might simulate what you could find on the Moon or Mars. They've got to tell us what type of things they're encountering in those layers, how deep the layers are, and how many layers are. It's all a mystery to them. They have no idea what's in there.
That's really cool. And I know industry plays a really important part in this as well. Can you tell me about that, and also why somebody who has no relation to NASA or space would be interested in getting involved?
Absolutely. We have several unique industry sponsors. First and foremost is Honeybee Robotics, who has been with us from the start. They provide judges, information about how we should set the challenge up. They provide actual funding for us, which is always appreciated. We also have Aircon and Buccal Stone Corporation, who provided in-kind materials that are inside the test bin. Some of those materials, some of those layers of the materials are in there. Pancopia provides in-kind turbidity testing, which is where they're looking at clarity of the water. We want teams to see how clear of water that they can extract out of those systems. And then finally, we have Proto Labs, who's new to us this year. Proto Labs provided in-kind sponsorships and up to $20,000 in custom-made parts for our students. And I think back to your question about, those that aren't really aerospace related, why would they support us? They know that what we're doing is important, and it's important to them, and they just want to be a part of that. Mike Buccal, who is the owner of Buccal Stone Corp., one of our sponsors, told me that when they were asked to help, he felt like it was his duty as an American. It was just a very patriotic response. He called our students that are out here future heroes that are working on real-world important problems. And he said providing some of the stone that would mimic what we might find on the moon was the very least that they could do.
I love that. Thank you so much for being with us, Stacy.
Absolutely.
And I'll let you get back to the competition.
Thanks,
There's a lot
Jessie.
going on. I'm going to throw it back over to Scott, and we're going to talk to some more of the teams. Over to you.
All right, thank you, Jesse. There's some really exciting stuff going on here today. For those of you at home who have just joined us, you are watching live coverage of NASA's Moon to Mars Ice and Prospecting Challenge. It is a mouthful to say, but it is worth the effort because what's going on behind me is very exciting. Ultimately, teams from across the country have gathered here, and they're attempting to dig through lunar and Martian soil, simulated lunar and Martian soil. We do not have the real stuff here today. And once they dig through that, they have to find ice, and they have to extract that ice and turn it into water, liquid water. That is not an easy thing to do. Why don't we go and chat with another one of these teams and get a better idea of what's going on and how they decided to create their design and solve this challenge. All right, I'm going to find my friend over here at Carnegie Mellon. How you doing? I'm doing good. What's your name?
Ismail Mercier.
Good to meet you. So tell me a little bit more about the design that we're looking at right here.
Our autonomous prospecting and extraction system is a 37.2 kilogram hammer drill. So basically, that motor right there hammers down this rod to break through the regolith and into the ice. So one of the bigger design complications, challenges that we had is that because we have such a light robot, we didn't put a massive, very powerful motor on it, and we weren't expecting such hard regolith. And we're struggling to get through. There's about a 6.5 inch slab of concrete in there, which is very difficult to break through. A lot of teams are struggling with it, and I think our motor is just not powerful enough to break through. But if we were to modify that and reinforce the robot a little bit, the idea would be we can break through with just using like high frequency hammering, and like some of the other teams are also implementing that. And then we have our water extraction system over here, which is a thermal distillation system. A lot of people have come up and talked to us about it because there's just these beer kegs, and they're wondering if there's anything fishy going on here. We're just telling them we have the Mars IPA going on. So basically how it works is that the water gets pulled out from the ice, pumped into one of these kegs, and heated up, and the vapor condenses in the coil back down into clear water. From there we can pump it out into the bucket as our clean water.
Awesome. So are you pretty much at a standstill now, or are you hopeful or adaptable?
I think we're basically at a standstill. The amount of concrete that we have under here we did not anticipate, and our machine is just not powerful enough to get through it, unfortunately. I think that in the future we're going to have to plan for, I guess, expect the unexpected is the key with this, and we did not expect the unexpected, and it was just a little too difficult for us to get through.
All right, lessons learned for year 4 of the challenge.
Exactly.
All right, well, I think we'll come back here for happy hour afterwards, yeah?
Yeah, sounds good. We'll welcome you.
All right, thank you. Well, I'm going to send it back over to Jesse, who's going to teach us a little bit about another team's drill design. Jesse, over to you.
Thanks, Scott. I'm here with Ben from Northeastern University. Thank you so much for being with us.
Hi.
And tell me a little bit about your design.
So what our design is it's not a rotary jackhammer like most of the other systems that you've seen here. What it is instead is just a penetrating jackhammer that goes straight into the ground. And the novel element of our system is that what it's able to do is it can not only jackhammer through the soil, but once we get down into the ice, the tip can remove, and in theory, with enough cables and wires, you could descend the tip of our tool deep into the ice, and you're only restricted by the length of cable as to how much ice you can collect. Once we collect this water, we pump it up through our peristaltic pump into a multiple effect distillation system, which should once again clean the water and pump out perfectly clear water to process.
And what are some of the challenges that you've encountered so far?
So prior to coming to this competition, our testing was focused on using standard concrete that you can pour in your home. This concrete is different. We should have gone with a testing that was more representative of this aerated concrete. And so we found that it's much more difficult to jackhammer through the concrete that's here because it compresses in on itself and becomes harder. And if you're able to turn on a rotary jackhammer, you can grind away that material and continue making downward progress. But with our just downward penetrating jackhammer, we can't do that.
And so I saw you guys taking your drill off and making adjustments today. What were you working on?
Yeah, so we've actually had a few parts that have broken. So we were trying to push the limit of our system in order to get downwards further into the soil. And what we did was we snapped one shear pin that was on the top holding the structure of the jackhammer, but also we had a problem when we were removing ourselves out of the overburden. The tip got stuck in the soil and we actually broke our cable mechanism. Fortunately, we had backups for these components because we anticipated these being our weakest links. We weren't intending for them to break, obviously, but we had them as a backup.
You were ready to go when the time came.
Yes, and we changed it out way quicker than I thought we were going to be able to do, but it went pretty well.
Well, I wish you the best of luck. Thank you so much for being with us, Ben.
Thank you very much.
I'm going to throw it back over to Scott. He actually has an important NASA expert who's going to check in on see how the teams are doing. Over to you, Scott.
All right, thank you, Jesse. I would like to introduce everybody out there, to one of the judges of this competition, Chris Jones. How you doing, Chris?
Doing great, Scott. How you doing?
I'm doing fantastic. I'm very excited to see all these designs today.
I am too. It's been really impressive watching everybody make it work yesterday and today, and we're seeing even more water collected today than we had yesterday, which is just fantastic news.
So we've had successes, we've had challenges. Why don't you show us something interesting that's going on right now in the field here?
All right, well, why don't I take you over to where Stevens Institute of Technology is working, because they're once again operating in what we call hands-off mode. So what they're attempting to do here is purely by operating their system remotely. Nobody is up on the machinery. Everything is being operated from a computer. They're drilling yet another hole to go down and melt and mine even more water. They've already had some successes today pulling water out here with this hands-off operation. In fact, I think they're thinking they've already pulled over a cup of water that way, which is the most we've seen yet.
So what's the difference between hands-off and hands-on?
So in hands-on, we let the teams get right up on top of their rigs and tweak any problem right in the middle of trying to solve it. It's very much about giving you the opportunity to make your system work and troubleshoot and get it to operate. Hands-off operation is much closer to what we would actually do at the moon or at Mars. Now the teams have to be able to operate everything from a computer control. They can't actually physically go up and touch their hardware. They have to rely on all the software they've put together in order to run their system and extract the water.
Okay, so I also understand that outside of extracting water, teams need to also create what's known as a digital core of the layers they're going through. Can you tell me a little bit more about how teams intend to do that?
Yes, so a lot of them are planning to use the data of the drill that they're working with and the measurements they can take of speed and power and the weight and the force they feel on the drill bit in order to estimate how many layers they're going through, how thick those layers are, and maybe even what they're made of. But other teams are attempting to use other techniques, such as looking at it, or some teams are even putting a microphone next to their drill and listening to the sound of it, and using that as a way to estimate what are the materials they're going through to build that digital core.
So we have different ways of extracting ice, different ways of getting through the layers, different ways of telling what the layers are. What does this diversity of ideas do for NASA?
So this is an opportunity for us to explore a whole range of possibilities in a way that might be hard for us to do one single idea at a time. Instead, we get the opportunity to test drive a bunch of different things with the students and then use the best of those worlds to move forward in our own plans.
This is some really exciting stuff here, Chris. Well, I'm going to let you get back to judging out there, and thank you so much for joining us.
Great. Good to talk to you, Scott.
All right, good luck. All right, I'm going to go throw it back over to Jesse, who's somewhere on the competition floor right now. Jesse, where you at?
Hey, Scott. I've been checking out all these different drilling designs. There is just so much going on around us. It's so neat to see. Some teams are harvesting ice and melting it in separate chambers. Some are melting it directly beneath the soil, and others are letting the ice condense into a gas and then converting it back into water somewhere else in their system.
All right, NASA's not the only one to recognize the importance of technology demonstrations like the ones we're seeing here today at the Moon to Mars Ice and Prospecting Challenge. Industry sponsors do as well. So why don't we go hear from one of those industry sponsors, Honeybee Robotics, about why they chose to get involved in this challenge. Jesse, I'm going to throw it back over to you.
Thanks, Scott. I'm here with Dean Bergman from Honeybee Robotics. Thank you so much for being with us.
Yeah, thanks for inviting me on.
And so I understand that Honeybee already has experience working off Earth. Can you tell me about that?
Yes, absolutely. We've been involved in many space flights. We've got a piece on all of the Mars rovers. We've done drills and tools for the rovers. Our Colorado office has sent electronics to space fairly recently with some commercial customers, as well as a JPL mission called OCO3. And then our Pasadena office is currently designing missions for some upcoming future flights.
And what is your involvement in the challenge here?
So I'm a judge today in the competition. So just going around, making sure, finding out who's going to win, see what's going on. And then also one of my roles was to make sure that the results that they were getting on their computer were actually accurate.
And so why would Honeybee Robotics want to get involved in a challenge like this?
Oh, this is really important for us. Outreach into the younger community is kind of the key in our foundation. We need these young engineers to come up and design the future for us. And, we'll be working with these guys pretty soon. So, we want the best for them. And I think this is all very exciting.
That's absolutely right. And I think if these young people are our future is bright.
Oh, absolutely. I totally agree.
And so you've had a chance to see all of these different designs.
Yes.
Any thoughts?
I think it's a difficult problem. There's a lot of pieces to this puzzle, and I think each team has at least one of those pieces. So as they all converge to a solution, I think we'll have a really strong solution to such a difficult problem.
Absolutely. I love that everybody's kind of approached this differently.
Yes.
And so you're saying that all of these ideas coming together is really the solution.
Oh, absolutely. I think so.
Awesome. Well, thank you so much for being with us, Dean. I really
thanks for
appreciate
having
it.
me. Thank
I'll let
you.
you get back to the competition.
Thank you.
Scott, over to you.
Okay, in case you are just joining us, we are coming to you live from NASA's Moon to Mars Ice and Prospecting Challenge. What is that, you ask? Well, university students from across the country have gathered here behind me to try and solve a dilemma. How do you get through simulated lunar and Martian soil and find hidden ice beneath it? Then when you get to that hidden ice, you need to find a way to extract it and bring it up to the surface and turn it into liquid water. This is not something that's easy to do, folks. I promise you. But these teams do seem up to the task. I'd like to go speak with somebody right now. Jerry Sanders. Jerry is in situ resource utilization technical expert for NASA. How you doing, Jerry?
Very good.
All right, you've got to tell me, what is an in situ resource utilization technical expert do?
Okay. Well, it's my job, first of all, to understand what in situ resource utilization is, but try to have an idea of the big picture. What are the resources we think we should be going for? How can they be used in future missions by NASA and commercial industry? Do we have the right investment strategy? What are the technologies and where do we get them? So a combination of things like that.
Okay, so all of these students here have created drilling systems and designs to extract water from simulated surfaces.
Yes.
How can these designs actually help NASA one day?
Well, as many people realize, there is no one solution typically if you have a problem. Mm-hmm. And so when NASA wants to work on something, they'll either turn to one or two or three contractors. Each one will pick a design or will do it in-house. And you're kind of constrained to already selecting a solution. The beauty of a competition like this is you're giving the same challenge to everybody, and interestingly enough, they don't all solve it the same way. So we have an opportunity to have 9 teams here try different things, and we get to see which ones happen to work.
I mean, it's a real diversity of ideas, really.
Yes.
So tell me about some of the more interesting concepts you've seen out there today.
Well, some of them are traditional. To extract water on Mars, the last several years, one of the main concepts has been called a Rodriguez well or a rod well. They use it in Antarctica. You drill into an ice sheet. If you have enough energy, you turn the ice into a pool of liquid water, and you slowly extract it as time goes on, dumping more heat into it. So several of the teams have taken different ways of trying to do that. Other teams have come up with different ways of how you drill through the material. Some are using rotary drills, some are using percussive instruments. And so some of them are very large in diameter, some are very thin. So it's a very interesting take on what might be the right blend of methods.
And that's the whole point of a competition like this, right?
Yes. Well, I mean, from a NASA perspective, we obviously want to try and see different things, but also it's part of NASA to help STEM. And looking at these students, you can see just the growth that has happened to be part of these activities, the lessons learned of getting out of the classroom and books, and the answer is always at the back of the book.
I mean, these students really must be having such exceptional experiences, meeting each other, meeting people from NASA, from industry.
The impression I've gotten is yes. Even the teams that haven't been necessarily as successful as they have wanted to be have all been extremely positive in how they've looked at this experience.
It's a benefit all around.
Yes.
So I want to talk a little bit more about in situ resource utilization. You've talked a little bit about how one day we could use water or water ice that's found on the moon or Mars, but what else could we find on other planets or even asteroids or comets that we could use?
Well, think of ISRU as a fancy way of saying learning to live off the land. Just like if we travel to another city or go camping or whatever the case may be, there's more to it than just drinking water. I have to have oxygen. I need to be able to grow food and make habitats. And I want to make spare parts at some point. So if you look at the moon itself, we hope that there's ice in permanently shadowed craters, but a lot of people don't realize that over 40% of the moon is oxygen. It's bound up in different minerals. So oxygen on its own is a tremendous resource. The metals, aluminum, iron, magnesium, all of those could be possibly used for additive manufacturing. And then the bulk material itself, we're learning how to 3D print habitats, which could be used for radiation shielding or landing pads. So there's a lot of resources that we can tap into and use for different ways.
This is very exciting, man. We have an incredibly exciting future ahead of us at NASA, I think.
Oh, I think so. And universities and commercial are going hand in hand with us on this journey.
Awesome. Well, Jerry, I really appreciate your time. I'm going to let you get back to judging out there.
Thank you.
All right, let's throw it back to Jesse. Jesse, to you.
Thanks, Scott. We are so excited to bring you live coverage from this year's Moon to Mars Ice and Prospecting Challenge, an important step in establishing a sustainable human presence on the moon. Now, just imagine what the researchers of tomorrow are going to be able to accomplish as we make the next giant leap for humankind.
Okay, Jesse, it is unbelievable the designs we've seen here today.
We've seen some really cool designs, and we've seen them collect water on camera.
We have successful teams out there. These teams, these university teams, have come up with some of the most truly unique and out-of-the-box designs to help solve this challenge. And it's not easy. One day, these designs could be used on the surface of the moon or the surface of Mars.
And if you want to learn more about NASA's return to the moon in 2024, you can visit nasa.gov.
Yep. So, for the Moon to Mars Ice and Prospecting Challenge, I am Scott Bednar.
I'm Jessie Wild. Thank you so much for joining us.
And remember, this is your space agency.
Get to know it.